Radicals are not always going to simplify to whole numbers, so we need to be able to simplify a radical by taking part of the factors and rooting that part, and maybe other parts are still left inside the radical. And so this uses the product rule for radicals to separate them. And I'll show you what I mean. For simplifying the radical here in a, the square root of 18, there is no square root of 18, for that's a whole number, right? So I need to split this up into two radicals, one that's a perfect square and one that is not. So 18 is 9 times 2. And that way I can simplify the square root of 9, that's 3, and the square root of 2 remains. So that's the simplified radical. Another way of doing this, also looking at the product rule, is to break 18 down to the prime factorization. So 3 times 3 times 2. And the index tells us how many factors we need for a root. So if this is understood to be 2, I need 2 factors to have a root of that number. So that's how this becomes 3 square root 2. And that's the way that I'm going to show these, because it's not always easy to see what that perfect square is. Like in B, the cubed root of 40. I'm not sure what that perfect cube might be. So I'm just going to take the prime factorization of 40. So that's 4 times 10, which is 2 times 5. Okay. So now I can see that I do have 3 factors of 2 to have a perfect root that comes out of the radical. What's left inside is 5. So 2 cubed root 5 is the simplified radical. For C, the square root of 14, I don't know if there's a perfect square in there somewhere. So 14 is 7 times 2. And I can see that there is not, because those are single factors and I need 2 factors to have a root here. So it stays square root 14, it doesn't simplify. For D, I've got the 4th root of 32z to the 7th. And so let me look at this 4th root of 32 first. So just this part first, because 32 is 2 5 times. So this index tells me I need 4 factors to have a root. So I have a root of 2. It's out of the radical, and the 2 remains inside the radical. But that's just the 32. What about the z to the 7th? I can do the same thing to visualize what that looks like. 7 factors of z, and 4 of them make a root. So that means z comes out of the radical, and how many z's are left inside? 3. And then I can multiply these together to get my final answer. For variables, it might be easier to look at this as a rational exponent. So z to the 7 over the index of 4. And then simplify that by turning it into a whole number part and the remainder fraction part. So 4 goes into 7 one whole time, right? And how many left over? 3. So that will leave a fraction part of 3/4. So altogether we have 2z, and inside the radical we have 2 from the number part, and z to the 3rd for the fraction part. So that would be the simplified radical expression here. In E, we have the cubed root. So I'm going to break this up into cubed root of 24 times the cubed root of a to the 9th times the cubed root of b to the 4th. I'm going to use the product rule to break that up into pieces. And first I'm going to look at the cubed root of 24. So 24 is 4 times 6. So if I'm looking for 3 of the same factor, I do have 3 of the same factor with 2. And what's left? A 3 inside the radical. Okay, so that's just the number part. Then I have the cubed root of a to the 9th. So let me just change that to the rational exponent. A to the 9 over the index 3. And that actually is a whole number. That's a to the 3rd. So that's all been rooted. Nothing is left in the radical. And finally, the cubed root of b to the 4th. So I'll change that to a fractional exponent. And this is an improper fraction that doesn't simplify to a whole number. So 3 goes into 4 one whole time. So that means one factor of b has been completely cube rooted. And how much is left over? 4 minus 3, so 1 left out of 3. So that means there's one factor of b left in the radical with the index of 3. So my final answer then, when I put the number, the a and the b all together, 2a cubed b cubed root of 3b is the simplified radical expression.